Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 5.1 on systems of linear equations in two variables. So let's start off by discussing, of course, what we mean when we say a system of linear equations in two variables. So first things first, a linear equation is an equation with variables to the first power plus or minus each other. So in the case of two variables x and y, a linear equation in two variables would be something that you could write in the form ax plus by is equal to c. Both x and y are to the first power here, but they can be multiplied by a coefficient. And there is also the potential for a constant term as well. This, by the way, is the standard form of the equation of a line that we first looked back in chapter 1. And a line is a linear equation. And so that's also what we're going to get when we ultimately graph these things. We're dealing with systems of equations involving lines. Now, a system of equations is when you have two or more equations simultaneously. So we're not just going to be working with a single line anymore. In this section, because we are dealing with two variables, we will be specifically dealing with two line equations. And the idea is that if we want to solve the system of equations, our goal is to find an ordered pair x, y, a value for both variables, that satisfies both of the line equations that we're working with. Not just one or the other, but both at the same time. So with that said, let's take a look at an example to illustrate this point. So in example 1, we're given a system of linear equations with two variables. We've got x plus y is equal to 1, and 2x minus 3y is equal to negative 8. And we're asked to determine if the ordered pair negative 1, 2 is a solution to the system of equations. All right, first things, make sure you remember that in an ordered pair, x goes first, y goes second. So they're telling us that we should have an x of negative 1 and a y of 2. Well, in order for this ordered pair to be a solution to the system, it has to make both equations true at the same time. So all we're going to do is plug it into both equations. If it makes them both work, it's a solution. If it doesn't, even if it makes one of them work, if it doesn't work in one, it's not a solution to the system. It has to work in every equation at the same time. So why don't we start with the top equation? X plus y is equal to 1. So if we plug in an x of negative 1 and a y of 2, we get negative 1 plus 2 is equal to 1, which is true. 1 is equal to 1. So the ordered pair works as a solution to the top equation, but we also have to check it in the bottom as well. We've got 2x minus 3y is equal to negative 8. I'm going to swap out the x with negative 1 and the y with 2, just like with function evaluation. And so this is going to give us negative 2 minus 6 is equal to negative 8. And since minus 2 minus 6 is a minus 8, that is also a true statement. Negative 8 is in fact equal to negative 8. And so it worked in both. So the question is the ordered pair negative 1, 2 a solution? The answer is yes, it is a solution. It works in both. And this is what we're going to be looking for throughout the section. The ordered pair that will satisfy both equations at the same time. We're going to begin by examining the graphs of systems of linear equations to determine the different types of situations that can occur with the number of solutions. And we have names as classifications for the systems depending on the number of solutions they have. So let's start by looking at the graph of just a single linear equation as opposed to a system to remind us what the graph actually is. The graph of a line is essentially the collection of all ordered pairs that satisfies the equation. Any ordered pair on a line would make the equation true. So as an example, I have graphed the line y is equal to 2x plus 3, and I have highlighted 3 of the ordered pairs on this line: negative 1, 1, negative 1 half 2, and 0, 3. And you would find that for any of these, if you plug in the x and you plug in the y, the equation would work. 0, 3 is really easy to see. So that's 3 for y, 0 for x. That would just give you 3 is equal to 3, which is true. Let's say we plugged in negative 1, 1. So 1 for y, negative 1 for x. This would give us 1 is equal to 1, which is true. So any ordered pair on the line is a solution to a single equation. Well, what about for a system of 2 equations then? In this case, we're dealing with the graph of 2 lines. So here I have graphed the equation 2x plus y is equal to 4, and I graphed this one in green, and I have graphed the line negative 2x plus y is equal to 2, and this one I graphed in red. And so what you would find is that any point on the green graph would make the top equation true, and any point on the red graph would make the bottom equation true. Well, if to be a solution of the system, you have to work in both equations at the same time, then what you're looking for are the ordered pairs, the points on both graphs. In other words, the solution to the system of equation is where the lines overlap, where they intersect. So you can actually solve a system of equations by graphing. You can just graph each of the equations individually and then look for the intersection between the graphs. And in this case, you should find that an x of 1/2 and a y of 3 would make both of these equations true at the same time. This would be pretty easy to verify. If you plugged it into the top equation, you would get 2 times 1/2, which would be 1, plus a y value of 3 would be equal to 4, which is true. 1 plus 3 is equal to 4. And if you plugged it into the bottom, you would have negative 2 times 1/2, which would be a negative 1, plus a y of 3 is equal to 2, which is also true. Negative 1 plus 3 is equal to 2. So keep this idea in mind as we start classifying these systems of equations. The solution to the system is where the lines intersect, where they overlap. Now, it turns out that because we're dealing with the graphs of 2 lines, meaning they can't bend or curve in any way, there are only so many different ways these graphs can interact with each other. What you're seeing here is one of the ways in which a system of equations can interact, and that's where the 2 lines intersect at exactly one point. In this case, the system of equations would have one unique solution. One half 3 is the only ordered pair that would make both of these equations true at the same time. If you tried anything else in the xy plane, it wouldn't work. In this case, we call the system of equations an independent system. Oftentimes, this is what we're hoping to see when we solve a system of equations, one unique solution that always works. But if you just have one solution, it's called an independent system. And we'll recap all of this in a slide a little bit later on when we talk about the other type of interactions. Now, let's say I tweak the equations of the lines a little bit. So now I have 2x plus y is equal to 4 and 2x plus y is equal to 1. Well, no matter what you plugged in for x and y, the left-hand side of these two equations would always be the same. But the right-hand side is different. There wouldn't be any ordered pair xy that would make both true at the same time. Graphically, this occurs when the lines are parallel to each other. In other words, they never intersect. Any point on the green graph would make the green equation true. Any point on the red graph would make the red equation true, but there is no equation to the system There is no solution to the system. And so in this case, we would say that the equation or the system has no solution. The name we use for the classification of a system of this type is actually the same as the name we used for individual equations back in section 1.1. We call this inconsistent. So this would be an inconsistent system of equations. There is one final way in which the graph of two lines can interact with each other. So this time I'm graphing the equations 2x minus y is equal to 2 and 4x minus 2y is equal to 4. And what you may see when you look at the graph is it appears there's only one line, but that's not the case. This is the graph of both lines. They just perfectly overlap with each other. In other words, these two equations represent the same line. They're multiples of each other, because if you just multiplied both sides of this top equation by 2, you would actually get the other equation. In this case, any ordered pair anywhere on this line would work in both equations at the same time because they perfectly overlap. So this would be an example of a system of equations that has infinitely many solutions. Right? Since this line keeps going forever in both directions, there are an infinite number of ordered pairs that you could plug in. Now, it's important to distinguish that this does not mean that anything works in the system of equations. For example, if you tried to plug in the ordered pair 3, 0, 3 for x, 0 for y, it would not work in either equation. It's not a solution. Infinitely many solutions doesn't mean everything works. It just means that there are infinitely many things that would work. As for the classification for this type of system, when we had one unique solution, we called it an independent system of equations. This time around, since one equation is just a multiple of the other, it's dependent on the other, we would say that this is a dependent system of equations. The two lines aren't different from each other, so they're dependent. So just compiling the information, a quick recap of the different things that can occur when solving a system of equations. You can either have one unique solution, which corresponds to an independent system, infinitely many solutions, which would be a dependent system, or no solution at all, which we would call an inconsistent system. Now let's talk about how to actually solve a system of equations without necessarily graphing. So how would we do this by hand through algebra? And we're actually going to cover two different methods for solving a system of equations in two variables in this section. The first of which is called the substitution method. And this is probably the more intuitive of the two methods, but it also is not going to work so well once we move up to more equations with more variables. So this is really a method that specializes in two equations with two unknowns. And the idea behind the substitution method is you're going to solve for one variable in one equation. So that's step one. It doesn't matter which equation you choose, and it doesn't matter what variable you choose. Whatever is easiest is usually what you go for. So you might choose to solve the top equation for x, or you might choose to solve the bottom equation for y. It doesn't matter, it all works. But once you have that, you essentially have created an expression for one variable in terms of another. So let's say you solve one equation and you get y is equal to 2x minus 3. Then what you can do is you can take this expression and plug it in for y in the other equation. So that's step two. You substitute what you just created into the other equation to get an equation in a single variable. You can't plug it back into the same equation you just solved for, because in that case, you would always just cancel everything out and get 0. So that's not helpful. You have to use both equations to solve the system. Once you get a single equation with a single variable, you're just going to solve for whatever variable you happen to be working with. It might be x, it might be y, it doesn't matter. That will be half of your final solution, because remember, the solution to the system is an ordered pair x, y. At this point, you'll know one of them. In order to find the other, you can just take that and plug it back into either of the original equations in the system. It doesn't matter. That will give you the value for the other half of the ordered pair. They'll both give you the same thing because it's where the lines intersect. That's what the solution is. And then the last thing that you might do in this type of problem is to double check your answer, just like we did in example 1, by making sure that it actually works in both equations. Right? So solve one equation for one variable, plug that into the other equation, solve for half of the solution, plug that back into the originals to solve for the other half of the solution. One thing I will note really quickly is that a lot of students coming in from high school learn a way of solving two equations with two unknowns where they will solve both equations for y first and then set them equal to each other. That is actually just a form of substitution. It's the same idea, it's just a more limited form of substitution, because solving for y is not always easy or nice looking. And so it's actually unnecessary for you to go through that extra effort. However, if that's the way you prefer to solve a system of equations, it does work. It is just substitution after all. So let's try out a few examples of solving a system of equations through substitution. Starting here in example 2, we've got the equation 5x minus 6y is equal to 23, and x is equal to 6 minus 3y. This is a really good example of a system of equations where substitution works great. That's one where you either have a variable with a coefficient of 1, because that means you're not going to make any fractions appear by trying to solve for it, or, especially in a case like this, you have a variable with a coefficient of 1 that is already solved for. So this is a problem that's custom made almost for substitution. We're going to find out very quickly that if you have a system of equations, if this were say 2x is equal to 6 minus 3y, substitution doesn't really work so great anymore at that point. And we'll swap into the other method in most cases. But for here, what we can do is, since we know x is equal to 6 minus 3y, we can just take that entire expression and plug it in for x in the top equation. This is a substitution, which by the way is the same as a composition of functions that we were looking at back in chapter 2. So I'm going to plug that into the top equation, which is going to give me 5 times x, which is 6 minus 3y, and then the rest of the equation is still the same. Minus 6y is equal to 23. Now I have an equation with just one variable y, which I'm going to solve for. So I'm going to multiply everything out, combine like terms, solve for y. All right, so on the left-hand side, we've got a minus 15y minus 6y. So a minus 21y. Subtract 30 from both sides. 23 minus 30 would give us a negative 7. And then divide by the negative 21. And a negative 7 over negative 21 would reduce to a positive 1/3. So that would be half of my final answer then. That's the y value, but we still need the x value. So now what I'm going to do is I'm going to take this 1/3 and plug it back into either of the original equations, usually whichever one you think is easiest. Having said that, if you're using the substitution method in particular, plugging it into the equation that you've already solved for the variable is usually the best choice. It'll give you the least amount of algebra to do. So if I plug this y of 1/3 into the bottom equation, we're going to get x is equal to 6 minus 3 times y, which is 1/3. 3 times 1/3 is 1, and 6 minus 1 is 5. So as an ordered pair, the solution to the system of equations x, y, make sure you're careful with the order, We have 5 for x, 1/3 for y. Now, because this worked out nicely and we got just a single answer like this, then this is an independent system of equations. This is the only solution. We'll see examples of the other shortly, but basically variables start canceling out and disappearing if it's one of the other two cases. This is what it looks like when everything works out nicely. Let's take a look at one more with substitution. So in example 3, we've got 2x plus y is equal to 9, and 4x plus 2y is equal to 10. So step 1, solve one of the equations for one of the variables. Usually just whatever you think is the easiest, it doesn't matter. In this case, because this y here doesn't have a coefficient out front, that's probably the easiest thing to solve for. So if I want to solve the top equation for y, I just need to subtract 2x to move it across to the other side. And now I can take this entire expression and plug it in for y into the bottom equation. So that would give us 4x plus 2 times y, which is 9 minus 2x, and that has to be equal to 10. All right, from here we've got one equation with one unknown. What happens this time around, however, is that we've got a 4x minus a 4x. Those cancel each other out, and what we get is 18 is equal to 10, which is just not a true statement. 18 is not equal to 10. This is what it looks like when you get an equation with no solution. If your variable cancels out and you get an untrue statement like this, that means that these lines were actually parallel to each other. They had the same slope. So no solution to this system, which means we would classify this as an inconsistent system of equations. Now let's take a look at the other method that we're going to be using to solve systems of equations. And this is the one that's going to carry forward when we start looking at section 5.2 with bigger equations, more unknowns. And this is a method that your book calls the additive method, but it's often also called the elimination method, because that's what we're going to be doing. We're going to be eliminating a variable through addition, essentially. And so the process of the elimination method is as follows. You start by writing both equations in standard form. Ax plus by is equal to c. You want to line everything up, because in a minute we're going to be adding the equations together, and we're going to be combining like terms. So you add x's with x's, y's with y's, and constants with constants. And lining everything up just makes that easier. Step 2, our goal is that when we add things together in just a second, we want one of the variables to cancel out. So if necessary, you want to multiply one or both of the equations by the appropriate number so that one of the variables has opposite coefficients, things that will cancel with addition. So if one of your x's is 3x, you could, for example, turn the other one into negative 3x. Then when you add them together, they'll cancel out. Sometimes just multiplying one equation is enough to accomplish that, but you can also multiply both equations by different numbers in order to make that happen. Just keep in mind that when you multiply an equation, you multiply both sides of the equation to keep it balanced, which means you multiply all three parts by whatever number you're interested in. Once you've got everything lined up properly so that one of the variables will cancel, you add the equations together. That will cancel out one of the variables, so you'll end up with one variable left. At that point, it becomes exactly the same as the substitution method. You're going to solve for that remaining variable. That will give you half of your answer. To find the other half, you plug that variable back into either one of the equations that you started with. And last but not least, you can, of course, as always, double check your answer by making sure that it makes both equations true. So let's try it out. We're going to take this system of equations in example 4 and solve it with the additive method or the elimination method. So the first goal is to write everything in the same form, ax plus by is equal to c, which is already done in this case. Everything is already lined up properly, so we can focus on the elimination step. Our goal is to get one of the variables, it doesn't matter which, to be ready to be eliminated. Same coefficient but opposite signs. Now it doesn't matter which variable you eliminate, but usually when you have a variable with a coefficient 1, just like in substitution, that's the one you want to target because it just makes your life easy. If I want to cancel out this minus 3x, I'm going to need this to be a plus 3x so that they add each other away. So to turn that into a 3x, I'm going to multiply both sides of the top equation by 3. That's going to give me 3x minus 12y is equal to negative 9. And our bottom equation is still the same. Negative 3x plus 5y is equal to 2. Now we're going to add these two equations together. This doesn't change the solution to the system because what you're doing is you're technically adding two equal things to each side of an equation. So it does preserve balance. And so we're going to combine like terms. The 3x's cancel. That was the whole point of the multiplication step. We have a minus 12y plus 5y, which would give us a negative 7y. And we have a negative 9 plus 2, which also gives us a negative 7. And so this is our one equation with one unknown. We can finish solving for y by dividing both sides by negative 7. And so we get y is equal to positive 1. Now we can plug that into either of the original equations to figure out what x needs to be. And it doesn't matter which, but again, I think the top equation looks a little bit nicer here. So I'm going to plug it into the top one. X minus 4 times y is equal to negative 3. So if I just add 4 to both sides, we get that x also has to be equal to 1. So the solution to this system of equations, xy, would be 1, 1. And because we got one unique solution out of this process, this is another example of an independent system. Let's try out a few more with the elimination method. So in example 5, we got the system of equations negative 2x plus 5y is equal to 14, and 7x plus 6y is equal to negative 2. So this is an example where you're going to want to multiply both equations by a number in order to get the coefficients to match up. So with that said, try pausing the video here and see if you can find the solution to example 5. Well, again, it doesn't matter which variable you target to eliminate. You could choose to either try and cancel the y's or the x's. Both will get you where you want to go. In this case, since the x's are already opposite signs, I'm just going to focus on them. It doesn't matter because you can multiply by a negative number as well if you need to. But let's see. I'm going to turn this top x into a negative 14, and I'm going to turn the bottom x into a positive 14. That should get us to cancel everything out. So I'm going to multiply the top equation by 7 and the bottom equation by 2. Now this is going to give us some pretty big numbers because we are going to get 7 times 14 here. So this is going to give us a minus 14x plus 7 times 5. So we would have a plus 35y, and this would be equal to 7 times 14, which would give us a 98. The bottom equation, double everything. So we've got a positive 14x plus a 12y is equal to negative 4. Be very careful here. If you miss multiplying one of the numbers, it will mess the entire problem up. You want to be very careful with this first step. So now I'm just going to add these together. Once again, my x's cancel. 35 plus 12 would give me a 47y. And a 98 minus 4 would give me a 94. Divide both sides by 47, and this works out quite nicely, which is not always the case. You'll get messy answers sometimes, but this one works out to just y is equal to 2, which is not bad. Now we can plug this back into either of the original equations to solve for x. And neither one is really nicer than the other. It honestly doesn't matter which you choose here. So let's see. Maybe I plug it into the bottom one this time. So that's going to give us 7x plus 6 times y, which we now know is 2, is equal to negative 2. So if I subtract 12 from both sides, negative 2 minus 12 would be a negative 14. Divide by the coefficient of 7, we get x is equal to negative 2. So the solution to this system of equations, xy, would be negative 2, positive 2. And so once again, because we got a single individual unique solution to this system of equations, this would be an independent system. Let's take a look at one more before we get into the word problems of the section. So this time around, we've got the system of equations 0.02x minus 0.04y is equal to 0.08, and x minus 2y is equal to 4. So first things first, anytime you've got a bunch of decimals like this in an equation, even before we start working on the elimination part, it's not a bad idea to get rid of those. So if I multiply both sides of this equation by 100, we can get rid of the decimals completely. That top equation would now just be 2x minus 4y is equal to 8, and the bottom equation is still x minus 2y is equal to 4. Now we can focus on the elimination. Again, it doesn't matter what variable you choose, so maybe just for a little bit of variety, I'll focus on eliminating the y this time around. So my goal is to get the y's to have the same coefficient but opposite signs so that they cancel out. So if that top y is a negative 4, I'm going to need this bottom y to be a positive 4. So I'm going to multiply the bottom equation by negative 2 to change the sign. That's going to give me, top equation I'm just going to rewrite out. 2x minus 4y is equal to 8. And then I'm going to have a negative 2x plus 4y is equal to negative 8. Question is, what happens when you try to add these two together? The x's cancel, the y's cancel, the 8's also cancel. So you get a statement that's true, 0 is equal to 0, unlike our no solution case earlier, where we had something like 8 was equal to 12, something that wasn't true. Now we get something that is true. When everything cancels like this, it's because these were actually both the same line. This is what it looks like when you have infinite solutions. One of these lines was just a multiple of the other. That said, we still need a way to describe the solutions that we're working with. And we do that in set builder notation. So we're going to write the set of solutions is x such that, and then because any ordered pair on one of our lines would be a solution to the system, we just write out the equation for one of our lines. It doesn't matter which, but because the bottom one looks a little bit nicer, we're going to choose that one. So it's going to be x such that x minus 2y is equal to 4. Any ordered pair that satisfies this would satisfy the whole system. Now that said, be a little bit careful with regards to your homework. Because MATLAB has to be able to check this answer, they're going to ask you to solve for one of the variables here. So on your homework, you might see something like x such that x equals blank. And if that's the case, you would just solve this line for x, and your answer would be x is equal to, if you add 2y to both sides, 2y plus 4, or they might have it pre-solved for y. It just depends on the problem. So the idea is still the same. You just use the equation for one of your lines, but they might ask you for the equation in a specific format. On the test, that's not going to matter. Just writing out the equation for the line is fine. Because this one has infinitely many solutions, this is an example of a dependent system of equations. For the last type of problem in this section, we're going to be dealing with word problems involving systems of equations. And these are a little bit on the tricky side at first. The goal is to recognize that in these word problems, they're going to be asking you to solve for two unknowns. Those are essentially the variables in your system of equations. They then give you two relationships between those unknowns so that you can solve for those two variables. The goal is just labeling the two unknowns and then building the system of equations from the word problem. So in example 7, we're told Althea has a higher income than Vaughn, and their total income is $82,000. If their salaries differ by $16,000, then what is the income of each? And so the first thing you ask yourself is, what is this problem ultimately asking for? And the answer is the income of Althea and the income of Vaughn. So let's give those letters. And you could always label X and Y, but truth be told, you can use any letter you want to. So why don't I use capital A to represent Althea's income, and capital V to represent Vaughn's income. That way we don't lose track of whose is whose. If we use X and Y, that works, but then at the end you would have to ask yourself, who does X correspond to and who does Y correspond to? So let's just get rid of that. That way we don't have to worry about it. Now our goal is to create two equations with these unknowns. The first thing we know is that their total income is $82,000, meaning if you added their incomes together, you would get 82,000. So that's the first equation in our system of equations, but we need one more relationship. The second thing we know is that their salaries differ by 16,000. In other words, because Althea's is the bigger number, if you took her salary and subtracted Vaughn's off, there would be a $16,000 difference. And that's really the most difficult part of this problem, because now that we've got it set up, this is a really easy system of linear equations to solve. I'm going to solve these by elimination because this is already perfectly lined up for elimination. We have a plus v on the top one and a minus v on the bottom. So if we just add these two equations together, a plus a would give us 2a. The v minus v would cancel out. And then we have 82,000 plus 16,000, which would give us 98,000. Then to solve for A, Althea's income, we just divide by 2. And so A would be equal to 98,000 divided by 2, or 49,000. Now in order to solve for Vaughn's income, you just plug that back into either one of the original relationships. Maybe we plug it into the top one. A plus B is 82,000. So 49,000 plus V is equal to 82,000. So if we just subtract 49,000 from both sides, we would get 33,000. So now we can answer the question. And by the way, again, really easy to double check this. Just make sure that it meets the conditions in the problem, that it satisfies both of the equations that we set up. But to actually answer the question, just putting a box around this is not good enough. We need to describe what we're talking about here. Althea's income would be $49,000, and Vaughn's income would be $33,000. Let's take a look at one more, and this one is tricky because it has an extra step on top of what we just did in the previous problem. We're told that at the book exchange, all paperbacks sell for one uniform price and all hardbacks sell for a different uniform price. So all hardback books sell for the same flat amount. If it's a hardback, it's just blank dollars, blank cents. We're told that Tanya got 6 paperbacks and 3 hardbacks for $8.25. Greta got 4 paperbacks and 5 hardbacks for $9.25. What we're asked here is what is Todd's bill for 7 paperbacks and 9 hardbacks? Well, the thing is that what we have to do first is actually figure out how much each of the 2 books cost. So this problem has 2 steps. The first step is to figure out the price of the books, and then the second step is going to be to use that information to calculate Todd's bill. So let's start off by setting up a system of equations just like in the previous example. What we ultimately need to know is how much the books cost. So let's introduce some variables. I'm going to let lowercase p represent the price of a paperback, and the word price there is important. Don't get it confused with the number of paperbacks that they're buying. And we're going to let h represent the price of a hardback book. Right, and so now we can set up our system of equations. From Tanya's bill, she bought 6 paperbacks, so 6 times the price of a paperback, and 3 hardbacks, so plus 3 times the price of a hardback, which added up to her total bill of $8.25. Similar for Greta, 4 paperbacks would be 4 times P, plus 5 hardbacks for 5 times H, and that equaled a bill of $9.25. So our first step is going to be to solve this system of equations for P and H, the price of the books. So substitution would be a mess here because we've got coefficients in front of every variable. Elimination is definitely the easier choice overall, but no variable is really easy to eliminate either. So it doesn't matter whether you choose to eliminate P or H in this case. Why don't I focus on H again? Because why not? So I want the H's to be the same coefficient but opposite signs. So maybe I multiply the top one by 5 to get a positive 15, and I multiply the bottom one by negative 3 to get a negative 15H. So if I distribute that through, the top equation is now 30P plus 15H is going to be equal to 5 times $8.25, which would be $41.25. And we multiply the bottom one by negative 3. Be careful with the signs. Everything flips. So it'd be a minus 12P minus 15H, which would give us a negative 27.75. And now I'm going to add these equations together. So 30 minus 12 would give us 18P. The H's cancel. And on the right-hand side, we get 13.5, or $13.50. which means now we would just divide both sides of the equation by 18 to solve for P. Which gives us 0.75. So in other words, at this book exchange, a paperback is 75 cents. In order to figure out the price of a hardback, we're going to plug this back into one of the original equations. Again, it doesn't matter which. So maybe I plug it back into the top equation. So 6 times P, which is 0.75, plus 3H is equal to 8.25. Subtract 4.5 from both sides. Divide by 3. And the price of a hardback is $1.25. So now that we figured out those two numbers, we can actually answer the question. What was Todd's bill? Well, we know that Todd bought 7 paperbacks, so 7 times 75 cents each. He bought 9 hardbacks, so 9 times $1.25. And so if we just multiply that out and add it up, we get that Todd's bill was $16.50. And that is it for section 5.1, systems of equations with 2 variables. Now, some things to keep in mind, types of problems in this section, pretty straightforward. It's either just solve a system of linear equations. We talked about 2 methods for doing that, substitution or elimination. I'm not going to be too picky, but you do want to make sure that you're comfortable with elimination because we're going to need it in the next section. And then there's also the harder type of problem in this section, which is solving word problems with systems of equations. And we went through the process of figuring that out. One thing I want to really stress here as we approach test 4 coming up soon, a lot of times I will pick systems of equations for the test, which, while not super simple, are also not unreasonably messy. The idea is that I want your test questions to not take an absurdly long amount of time. That said, every now and then I'll have a student who gets to the right answer through guess and check. I'm not interested in that. My goal is to see if you understand the process for solving these for when things get a little bit messier. So let's just make this very clear right now. For systems of equations on the exam, guess and check will receive no credit. I'm not going to care if you solve using substitution or elimination, but if I see no work, or if I see that you're just guessing and plugging things in for X and Y, you're not going to get any credit for that. So please keep that in mind. I don't want anyone spending a lot of time on a test question with that strategy only to find out later on that they're not going to get credit for it. All right, so just if you're not sure how to work the problem, if you have the extra time, try to figure it out. Try to see if you can solve it through substitution or elimination, or if you don't, then just don't even try guess and check. It's not worth the time. I could always pick problems so messy that they couldn't be solved through guess and check, but again, my goal is to just not make problems really messy for everyone to try and prevent a few people from just trying to brute force their way through a problem. All right, and so with that said, as always, if you guys have any questions about the material, please make sure you let me know, and I'll see you in the next video.